Okay, so another lecture. This time we are going to talk about integrals. So essentially I am going to talk about complex integrals, right? So integration along some curve C of f of z dz, right, where z is a complex number, right? So, but before that, I would like to start with what is known as line integral, because all these concepts will be required. So I'm going to talk about line integral in the reals, okay, and also double integral. So it's again I'm going back to especially two variable functions, okay. I think this portion I left when I was talking about two variable functions. So now I'm going to again relook at those functions with in terms of integration. So what is known as integration along a curve for a two variable function? How do you define all those kind of things? So basically line integral, curve integrals and double integral, that is what I am going to cover. And after that then I will give you an idea of complex line integral and then how it connects to the classical one, especially two variable functions, okay. So let me start. Okay, so integrals. First of all, I am going to recall real integral, which you know, especially Riemann integral. And here, so if you remember, we have given a definition of definite integral a to b f of x dx. If y is equal to f of x is a curve, for simplicity I have assumed that it's just a one loop kind of thing, and then we took from x equal to a to x equal to b area under the curve, right? Right, and that you know, right? So same thing can be done. So there, so you may take, so if you want to compute the area, you sort of divide this area into small rectangular strips, right? And then you compute this area of that strip, and then the point to compute the area, of course you need to look at the width of the strip and the height, and height may vary depending upon where you take the point, right? And so this height will give you some sort of approximation, but when you do division of infinite division kind of thing, actually it is approximately exact height of that point, okay. So just let me recall that. So definite integral a to b f of x dx, where f of x is a function from closed interval a and b, two reals. So f is a function, it's a single valued function. Right? So for every x in closed interval a comma b, the function is defined. Now what I do, I take this interval a closed interval a b and divide it into, so I say that a less than x naught less than x1, I do a partition of this. So this is a partition P. Right. So take the interval and I'm partitioning the interval, right? Okay, fine. So something like this, your x naught and this is your xn. Somewhere here there is x1, x2, somewhere here there is xk minus 1, xk, and so on. Right? Sorry, this is not there. So then we take xk star, in each subinterval, xk minus 1 and xk. So suppose here is xk star here, somewhere here is x1 star, and so on, right? So what I have done, divided the whole interval between A to B, certain number of points, finite number of points. Then for each subinterval, because now I have to compute the area, right? So basically I need to get the width and the height. So I am taking a point xk star in between, right? Now if this is the partition I have done, third what I need to do, let this length, is the length of the longest subinterval. Okay. So there are intervals, okay. Someone could be longest one. And of course I have taken xk star in this subinterval. Now if we form the product f of xk star, what will be the f of xk star? Height of that subinterval, I mean that area, when you will compute the area, right? F of xk star is the height times width, right? Delta xk is the width times height, f of xk star at that point. So this is true for each k, k is equal to 1, 2, whatever. So I can form this sum. I am not drawing any picture here, I am just writing everything, so because picture you have already seen so many times, I am just recalling it. K is equal to 1 to n, f of xk star times delta xk. Right? So this will be the area under that curve y is equal to f of x. Right? Now obviously this will be an approximate, because at some point that height could be above the actual height or below the actual height, right? So now what I need to do, take the limit as n tends to infinity. So when the subdivision becomes very, very small, actually we get the actual value of the area, right? So we have definite integral a to b f of x dx as limit length of the largest partition goes towards 0, 1 to n, f of xk star delta xk. Right? So this is a formula, right? What is xk star? Point in that subinterval, right? Delta xk, width of the subinterval. F of xk star, height. So height into this will give you the area of that strip, and you sum it for all endpoints, right? For all these subintervals, and then you take this limit, right? Length of this largest partition goes towards 0. Okay, so this already. We have done this, right? Some time back. I'm just recalling for single variable. Now the same idea I am going to do it for double variable. Okay. But before that, I have to give you some idea about the different types of curves that we call. So let me first define what are the different curves. Suppose C is a curve, right? And we can find a parametric representation like x is equal to xt and y is equal to yt for this curve. Parametric equation, right? C is a curve. By the way, can we do parameterization for each curve? Is it possible to find parametric for every curve? Most of the common curves that you know, probably circle, hyperbola, parabola, right? All these can be parameterized. You can find a parametric equation as well, right? For example, for circle it is x equal to cos t sin t, right? For t is or theta, whatever you call, right? Some parameters. Hyperbola, parabola, all these things. Basically, curves for which you can find parameterization are known as curves of genus 0. That's some geometrical point of view I am telling you. Genus is a measure of the smoothness of the curve. So for all these you can do parameterization. So a nice t time problem for you. Give an example of a curve for which we cannot find a parametric equation. समझ में आ रहा है ना? जिसके लिए हम पैरामेट्रिक इक्वेशन ना निकाल पाए, ऐसी कर्व का एग्जाम्पल देना है. ओके, थोड़ा सोचोगे तो मुश्किल नहीं है. यू विल नो कि व्हेन वी विल नॉट बी एबल टू फाइंड, राइट? सो गिव एन एग्जाम्पल ऑफ ए कर्व फॉर विच वी कैन नॉट फाइंड पैरामेट्रिक इक्वेशन. ओके, सर्किल, पैराबोला, हाइपरबोला, ये सब का जो है ना, यू कैन फाइंड इजीली, राइट? सो कॉमन कर्व्स हैं. We need to find something uncommon. By the way, that kind of curve is very useful when you use your credit card or debit card. Actually, that curve is used. Okay, so now you know that's something very important. Okay. So now, so in this curve, suppose we have parametric equation. So now what we can do, I can do what is known as x of a, y of a, you know, that is initial point. Right? Call it A, capital A. Initial point of the curve when we take t is equal to a. Right? Similarly, we have this is the terminal point. Terminal point or final point, call it B of curve C. Right. So there is a curve, we are able to do a parametric equation, then for t is equal to a and t is equal to b. So t is equal to a will give you initial point on the curve, t is equal to b will give you the final point or terminal point on the curve, right? Fine. So now some nomenclature or some properties I would say. C is called a smooth curve. If dx over dt and dy over dt are continuous. Okay, if these derivatives are continuous, dx over dt and dy over dt, then the curve is known as smooth. And of course, I forget to, they should not be simultaneously 0. One more condition, not simultaneously 0. These derivatives should not be simultaneously 0, right? Second, C is known as piecewise. Maybe I should. So I can give you first definition actually. I mean first picture. This is what? A smooth curve. You can see. Okay. Second, we wanted to talk about C is a piecewise smooth curve if it consists of finite number of small curves, C1, C2, Cn. These are small curves join end to end. So a curve is said to be piecewise smooth curve if it is joined by finite number of curves C1, C2, Cn, which are also smooth. So as an example, starting from A, this is yours A, and this is your end point B, C1, C2, C3. Piecewise is smooth, right? So for each piece it is smooth, right? Now we talk about simple curve. C is said to be simple curve. If C does not cross itself, except possibly at end points. I mean except possibly at t is equal to A and t is equal to B kind of. Okay. So for example, this is a simple curve also. Right, it is not crossing it itself. Similarly, this is also simple curve. This is smooth, I mean piecewise smooth and simple curve, right, which does not cross itself. Then fourth, C is said to be closed curve if A is equal to B, right. This is simple closed curve. You know, if initial point and final point are same, right? I mean they sort of combined, right? So they got simple closed curve. Oh, so this is closed curve and simple closed curve. I mean similarly we can say simple closed curve, a related concept. Simple closed curve if it does not cross itself and A is equal to B, right. So simple closed curve. Okay, what about this curve? This is a closed curve. This curve is closed because t is equal to A and t is equal to B is same. But is it simple? No, because it is crossing itself. Okay, so I think we are ready. These some basic nomenclature actually they use. Okay, simple curve, simple closed curve. Now I'm going to use this nomenclature quite often when I'm going to integrate a function along some of these kind of curves. Okay. अब ये थोड़ा सा नया कॉन्सेप्ट आएगा, हालांकि आइडिया सेम ही है, आइडिया में कुछ नयापन नहीं है, बट आई एम गोइंग टू डिफाइन व्हाट इज नोन एज लाइन इंटीग्रल. In the plane, or we also call it curve integrals. Okay. So suppose g is a two variable function. G is a two variable function, right? Now two variables x and y defined at all points on a smooth curve C that lies in some region of the xy plane. Okay. तो g is a two variable function, that is okay. Extra चीज हम क्या ऐड कर रहे हैं? These two variable x and y defined at all points on a smooth curve C. And x and y are, you know, that lies in some region of xy plane. Okay. जिस तरह की अभी कर्व्स की हमने बात करी है, right? So x y are, so two variables x y defined at all points on a smooth curve C. Okay. And suppose we have a parameterization for C as a parametric equation. X is equal to x of t, y is equal to y of t, a less than or equal to t less than or equal to b. Okay. G is a two variable function. ठीक है. X and y जो points हैं, they are defined at all points on a smooth curve C. C has a parametric representation. Right. Now जो भी हमने रीमान इंटीग्रेशन के लिए किया है, similar definition I am going to use here. Let us see. Let P be the partition of closed interval a comma b into subintervals tk minus 1 and tk of length delta tk is equal to tk minus 1. So now you see, अभी previous इंटीग्रेशन में हम क्या कर रहे थे? x को सब डिवाइड कर रहे थे, right? x को सब डिवाइड कर रहे थे, पार्टीशन कर रहे थे ना, x1 x2 xn एंड सो ऑन. अभी हम क्या कर रहे हैं? इस पैरामीटर को सब डिवाइड कर रहे हैं. नाउ यू सी, दिस विल ऑटोमेटिकली इम्पोज पार्टीशन ऑन x and y, right? Because x is a function of t and y is a function of t, right? t पैरामीटर को हम पार्टीशन कर रहे हैं. ओके. So we are doing something like this: a is equal to t naught less than t1 less than t2 less than tn minus 1 less than tn is equal to b. So let us see an example, then it will be, I mean, picture basically. This is your delta xk along x-axis. This is along y-axis delta yk, and here is a typical point xk star, yk star, and this is the partition delta sk. So what happens, as soon as you partition the parameter t, it will induce partition on the curve C, right? Curve C का partition हो जाएगा. So I think I should have. Right. So once we partition the parameter t, because x is a function of t and y is a function of t, there will be induced partition on x and y. So वो ये हो गया, right? उसमें सब इंटरवल की लेंथ यहाँ पे ऐसे आएगी, डेल्टा x के आएगी, यहाँ पे जो पार्टीशन होगा. सिमिलरली यहाँ पे होगा वो डेल्टा y के आएगा, और कर्व का भी पार्टीशन हो जाएगा, right? Because curve is defined by x and y only, right? Parametric equation. So there is a partition. Here the length is delta sk. So partition is, so यहाँ पे जो partition आएगा वो क्या आएगा? x0, x1, x2, x3 and so on. यहाँ पे जो partition आएगा y1, y2 and so on. And here क्या आएगा? s0, s1, s2. तो curve का partition कर रहे हैं, उसको हम s parameter से denote कर रहे हैं, right? So all the three partitions will come. As soon as you partition the parameter t, it will induce three partitions. X along x-axis, y-axis, and along the curve, right? Any question at this point? So basically so I should say in a more appropriate manner, as soon as we do a partition on t, it induced a partition on the curve, okay, and that gives you a projection. So this is a projection on x-axis and y-axis, which is a partition, which induces a partition on x and y-axis anyway. So now, again, we can say that this is the length of the largest subinterval. Just like in the previous case, right? So if we choose a point, xk star and yk star on each sub arc of C. So C has many sub arcs, right? These are sub arcs, right? And so a typical point I am choosing here xk star, yk star, because curve is represented by x of t, y of t, right? So xk star, yk star I am taking in this sub interval, I mean sub arc actually, right? So now we can do three products we can form. So if you recall here, we were able to do what? हमने केवल x axis में partition किया था closed interval AB को, and then we formed this product, right? This was the height times this width, right? Now same idea ko I am carrying there. Now I have partition T, it induces a partition on the curve and also on x-axis and y-axis, right? So how many products I can form now, you see? So I can actually now form the following products. G is the function xk star yk star times delta x, G of xk star yk star delta xk. Similarly, we can form G of xk star yk star delta yk, and similarly we can find G of xk star yk star delta sk. वहाँ पे तो हम एरिया निकाल रहे थे, राइट? यहाँ पे एटलीस्ट आई एम जस्ट डूइंग सिमिलर एनालॉजी, राइट? वहाँ पे जो इंटीग्रेशन का डेफिनेशन था, राइट, इट वाज एक्चुअली एरिया अंडर द कर्व, राइट? सो हमने वैसे ही 3 प्रोडक्ट्स फॉर्म कर लिए, राइट? वहाँ पे भी क्या किया था, जी को फंक्शन को इवोल्यूट किया था उस पॉइंट पे, राइट? एंड देन वी मल्टीप्लाइड विद द विड्थ. समथिंग विल कम आउट ऑफ दीज 3 प्रोडक्ट्स. So we can form the summation k is equal to 1 to n, summation k is equal to 1 to n. Arey yaar, so this is too problematic for me. And summation k is equal to 1 to n. I can form the 3 sums, right? So now when we take the limit of the largest subinterval goes towards 0, the length of the partition goes towards 0, length of P goes towards 0, actually we will get something, and that's what I am going to define now. So first definition, the line integral of G along C with respect to x is defined as limit this goes towards 0, summation k is equal to 1 to n, G of xk star yk star times delta xk. So line integral of the of the 2 variable function along the curve C with respect to x is this, right? Very natural definition. Similarly, we can define the line integral of G along C with respect to y is right along x with respect to x with respect to y. Okay, now what, एक और sum रह गया, right, along that curve. So third, the line integral of G along C with respect to arc length S is given by integration along C G of x comma y ds is equal to limit summation k is equal to 1 to n G of xk star yk star delta of sk. Right. So what we have done, जो डेफिनेट इंटीग्रल में हमने एरिया अंडर द कर्व निकाला था और जो फॉर्मल डेफिनेशन जैसे डिफाइन किया था, राइट. सी मेनी टाइम्स मैथमेटिशियंस दे जस्ट टेक द आइडिया और सिमिलर आइडिया में क्वांटिटी डिफाइन कर दी विदाउट वरिंग अबाउट व्हाट वी आर कंप्यूटिंग. ओके, एंड आई थिंक आई हैव शोन यू दैट ओनली, राइट. टुक द आइडिया फ्रॉम देयर, टू वेरिएबल फंक्शन लिया, पार्टीशन किया कर्व को, राइट, एंड वी डिफाइन दीज थ्री कर्व्स, राइट. अब ये क्या, इसका कितना फिजिकल सिग्निफिकेंस है कुछ तो तुम देखो ना. जस्ट चाय के समय सोचो इसका कुछ फिजिकल सिग्निफिकेंस है कि नहीं है, क्या है, राइट. ओके, व्हाट वी डू, डेफिनेशन में कोई इशू नहीं है, राइट. जो वहाँ पे डेफिनेशन थी हमने उसको एज इट इज कॉपी कर दिया यहाँ पे, राइट. एंड वी डिफाइन द इंटीग्रल्स, राइट. दीज आर नोन एज लाइन इंटीग्रल्स. ओके, वेरी इंपॉर्टेंट कॉन्सेप्ट. You will see that these line integrals have connection with complex variables as well. So मैं बाद में बताऊंगा, but anyway. Okay, so this is for some of the I think now I can do some simplification here. So actually, to find line integrals, so if we can do that, so there are two methods. First, when C is a parametric curve and second when C is defined by explicit function. This is case A, this is case B. So in case of case A, integration along C, g of x y dx is nothing but a to b g of x t y t x dx over dt times dt, right. Similarly, integration along C, g of x comma y dy is equal to integration a to b g of xt comma yt y prime of t dt. These are some simplifications. I mean, sometimes these are quite often used. So here C is given by parametric way, actually x equal to xt and y is equal to yt. So you can do the we can discuss case B later on. Let us do one example before we close. Find out x y square dx. Where path of integration C is the quarter circle, we call it as. So I should say that defined by x is equal to u cos t, y is equal to u sin t, 0 less than equal to t less than equal to pi by 2. This is the curve actually given to you. Quarter circle, right? This is our C. T is equal to 0 will give you 4 0 and t is equal to pi by 2 will give you 0 4. So this is a quarter circle x is defined by u cos t and y is equal to u sin t. T varies from 0 to pi by 2, that parameter. So it's a quarter circle, right, from here to there. So t is equal to 0 will give you what? 4 comma 0, and t is equal to pi by 2 will give you 0 comma 4. Along this curve you have to find that integration, line integral. So I just now I showed you the parametric, because the parametric representation is given, it's very easy to compute. This is nothing but so I can compute. So if x is this, what is dx? Minus, yeah, actually this is 4, actually, I'm sorry, this is 4. This is all 4, okay, this is not u, 4. Dx is 4 times sin t dt. So the whole integration c x y square dx will be 0 to pi by 2 4 cos t 4 sin t whole square minus 4 sin t dt. I have just substituted this value here, और ये तो simplify करके you can find out this value is minus 64. So okay, so this is integration along c xy square dx. Similarly, you can find out integration along c xy square dy and integration along c xy square ds. क्या निकाल के दिखा सकते हो क्या आएगी वैल्यू? सब्स्टिट्यूट करना है, x इक्वल टू 4 cos t ना. अभी जो मैंने पैरामीट्रिक कैलकुलेशन का फॉर्मूला बताया ना, यू हैव टू जस्ट अप्लाई देयर, राइट? स्ट्रेट फॉरवर्ड सब्स्टिट्यूशन. So in this case here, B case, dy is equal to 4 times cos t dt. So integration along c xy square dy is equal to 0 to pi by 2 4 cos t 4 sin t whole square 4 cos t dt. Simplification will give you 16 pi. That I leave it to you, right? Similarly, last one भी मैं लिख ही देता हूँ, I think, right? Last one, when we want to compute c xy square ds. So first of all, I need to find ds. ds will be square root of dx over dt whole square plus dy by dt whole square, right? So this will be 16 times sin square t plus cos square t is equal to 4 dt. So this whole value will be 0 to pi by 2 4 cos t 4 sin t whole square 4 dt, and this turns out to be 256 by 3, right? So this is all for line integral. I have given you the formal definitions and also one example. When you want to compute line integral along with respect to x, line integral with respect to y, line integral with respect to the arc length s. Okay. So iska physical significance I leave it to you for you to look at it. That's all. Next we are going to do some more things.